I'm Simron Thapa from Louisiana State University. I'll present our work on dynamic fluid surface reconstruction. Dynamic fluid surfaces are fast evolving and cause complex distortions due to refraction. For these reasons, it is very challenging to recover the 3D fluid surface from a single refraction image. Further, a single viewpoint is under constraint. Therefore, existing solutions for fluid surface reconstruction use multi-view systems or customized optics. However, these systems are difficult to build and calibrate. In this work, we present the first attempt to use a deep neural network for recovering fluid surfaces from a single viewpoint. We designed physics-based loss functions for network training. Due to the lack of fluid data, we synthesize a large fluid dataset using physics-based fluid modeling and rendering. Further, our network is validated on real captured fluid images. Our fluid surface reconstruction network consists of two subnets: an encoder-decoder based convolutional neural network for per frame depth and normal estimation, and a recurrent neural network for enforcing the temporal consistency across multiple frames. Our CNN subnet takes the refraction image and reference pattern to estimate the depth and normal by analyzing refractive distortions. Our network considers physics-based loss that models the fluid refraction. We also use a depth to normal loss to enforce consistency between our depth and normal estimations. To make our network more robust for fluid body with various depths, we design a scale loss function. Besides these, we adopt widely used depth and normal loss functions. Please see our paper for details of these loss functions. Our RNN subnet refines the depth and normal estimations by enforcing the temporal consistency. We concatenate multiple scaled depth and normal maps estimated by the CNN subnet and use it as the input for the RNN subnet. We use the convolutional LSTM layers to construct our RNN subnet. As it's challenging to capture fluid dataset with physical devices, we use physics-based modeling and rendering to synthesize a large fluid dataset for our network training. Our dataset contains over 45,000 refraction images from 75 fluid sequences. We use various reference patterns and we provide the ground truth depth and normal maps for each fluid surface. Our dataset will be made available on our project website. We train our network with 1.7 million parameters on 40,000 images from our dataset. The training time is around 6 hours. Our CNN and RNN subnet are trained separately. We first perform synthetic experiments on 1,000 images from our dataset. Our testing images do not overlap with the training ones. This result shows a shallow water wave. We compare the recovered surfaces with the ground truth ones. Here is another result on deep water waves. We compare our network with the state-of-the-art depth prediction networks. We can see that our network achieves the best performance. Without the physics-based refraction loss and the temporal consistency constraints, other depth prediction networks do not work well on fluid scenes. We do ablation studies for verifying the importance of each of our loss functions and the recurrent layers. We see that our final version outperforms all the intermediate ones. We also perform real experiments to evaluate our network. Here shows our experimental setup and reference pattern that are used. Our water is around 10 cm deep. We place a reference pattern at the bottom and mount a camera on the top to record videos of water waves. Here we show a reconstruction results on real data. This is a ripple wave with damping effects. This is a wave that is randomly disturbed. To validate our reconstruction, we compare the re-rendered refraction images with the real captured ones. We can see that the distortions are highly consistent. Thank you for listening. Please visit our project website for our code and dataset.